Hey everybody, Dr. P here with a video on how to deal with triple integrals in different coordinate systems. I got a lot of questions on your cards this week about a couple of things. Number one, how to set up a triple integral in a certain coordinate system, either Cartesian, cylindrical, or spherical. And two, when you can set up the integral in any of those coordinate systems, how do you decide which one is the best to use? So I thought the best way to explore both of those questions would be to do an actual problem. This is just a problem that I've never seen before that I've put up on the board. You have a cone. It's a solid cone, which I'm calling W. The height of the cone is 2, and it's the usual shape where the lateral face of the cone is at a 45-degree angle with the xy plane. And over that region W, I want to integrate the density function delta of x, y, and z equals the square root of x squared plus y squared plus z squared. And we're going to try to compute the integral over W of that density function. Now, I just found this problem. I don't know how exactly I want to approach it. I don't know the best way to approach it. I don't know whether I should set it up in Cartesian, cylindrical, or spherical. So I'm just going to start by trying something. I'm going to start by trying Cartesian coordinates and see where that takes me. So let's give it a go. So to set this up in Cartesian coordinates, I know that my integral is going to look something like this, and I'm just going to give myself a lot of space to work at first. I know that I'm going to have 3 integrals, and my integrand is going to be square root x squared plus y squared plus z squared. And then in Cartesian coordinates, my dv, my volume element, is going to be dz, dy, dx, or some other ordering of those. I could use dx, dy, dz, but I always like starting with dz, dy, dx and seeing if that'll work. If not, I can always try something else. The reason, by the way, that I like starting with dz on the inside and seeing if that'll work is with a lot of these solids, you notice that there is a clear lower surface, that's this lateral surface of the cone, and there's a clear upper surface of the solid. And in this case, that's true. I have an upper surface that holds up for the entire region, and I have a lower surface that holds up for the entire region. In this case, my upper surface is just the plane z equals 2 because it's a flat horizontal plane elevated 2 units above the origin. Okay, so that's my upper surface, and that's going to be the maximum value of z no matter where x and y are. So I'm going to write z equals 2 here. I always like writing the variable names just to remind myself what it is I'm doing, and I recommend you do it too until you're really super comfortable with these. Okay, so my upper height is z equals 2. My lower height is going to be given by the actual cone surface itself. The cone surface is given by the equation z equals square root x squared plus y squared. That's the standard one, and I haven't done any shifting or stretching to it, so that should be it. So that's my lower limit of integration for z. Z equals square root of x squared plus y squared. So now I've got to think about x and y. Now, what some of your instructors do that I find really helpful here is they think about what the shadow of this entire object would be in the xy plane, because at this point I have to figure out what are the values of x and what are the values of y that I'm integrating over. Now, a common student mistake is to write down something like this. I know that x goes from all the way from back at -2 to +2, and y clearly goes from -2 to +2. Problem is that doesn't quite work, because if I set up x going from -2 to 2 and then y going from -2 to 2, no matter what the value of x is, the region in the xy plane that I'm integrating over is a square. It's a square with side length 4. And I know that that shouldn't be exactly what I'm doing here, that this thing doesn't sit over a square in the xy plane, it sits over a circular region. So these two integrals here need to describe what that circular region is that this solid sits over. Okay, I think I've got the x equals -2 to +2 right. I feel pretty good about that one. But to figure out what my y's are, I'm just going to do a little reality check here. I'm going to draw a picture in the xy plane of where this solid sits. That's going to be over a circle of radius 2. So this is 2 and this is 2. Now when I look at this region, I know that I wouldn't describe this region if I were doing a double integral. I wouldn't describe it by saying x goes from -2 to y. X goes from -2 to 2 and y goes from -2 to 2. Now I do something different. I would say, let's let x go from -2 to 2, just like we've done here, and let's let y go from this lower semicircle to the upper semicircle. Now that circle is defined by x squared plus y squared equals 2 squared, for 4, which means that y is going to be plus or minus the square root of 4 minus x squared. Well, the minus gives me the lower semicircle, and the plus gives me the upper semicircle. So that tells me what these other two limits of integration ought to be. They should be y equals negative square root of 4 minus x squared, and y equals positive square root of 4 minus x squared. And now what I have is an integral that says, okay, let's let the value of x run from -2 to 2, and then for a given value of x, let's let y run from this lower semicircle to this upper semicircle. And then once we fixed x and y, let's let z go from this cone all the way up to this horizontal plane at the top. That's what this integral is doing. So now I think I have a successful setup in Cartesian coordinates. Let's try evaluating. By the way, the idea of putting the picture in the xy plane to figure out the region is a trick that I got from some of you in class. And I think it's a great strategy, so keep doing that if you're doing it already. Okay, let's look at this integral here. I've got some pretty funky limits of integration here. Certainly doesn't look friendly. And I've got this integrand here, square root of x squared plus y squared plus z squared. And I'm going to try to integrate this with respect to z. Well, you know, if I went to my integral table in the book and looked for the integral of a square root of a constant plus z squared, because for right now, as far as we're concerned, x and y are constants, I could probably find something that would work. I'm not sure I like what I see there, so I don't think I really want to do this. I think that my setup in Cartesian is correct. That is, this is an actual integral that would evaluate the mass of this solid, but I just don't feel like doing it. So I don't think I'm going to do that. Here's what I think I'm going to do. I'm already at 7 or 8 minutes on this video, so I'm going to cut this video off and start a new video in which I try cylindrical coordinates, so stay tuned.